Morning, everyone. So my name is Ryan, and today I'm going to talk about a paper in 2021 by OpenAI. So before we talk about the paper, as an introduction, I want to show you how. Let's look at the traditional supervised learning and maybe some limitation of it. So right here, I have a very simple task. I need a model to tell me whether this picture is a cat or a dog. So in normal setting, we need to collect a bunch of photos of cats and dogs. And we will have a loss function that tells the model, like, hey, this is the right class. If you go this way, you will have the lowest loss. If you go to that cat class, you will get punished with a larger loss. And after some times of training, we will have a ready-to-use model that can tell the difference between cats and dogs. So this is fairly normal. So right now I want to change the object a little bit. So I want the model to tell me this is a cartoon dog instead of a real dog picture. So this time we need more class labels. Besides a normal class, we need a new class called the cartoon dogs. And we tell the model to go this way. This is the class that will have the lowest loss. Now, okay, this time I want to change the object again. I want the model to tell me this is an orange cartoon dog. So right now I need I need your guys' help. So you can help me answer this question. What do you think that what else class label do we need to add to it in order to help the model to do this classification? So right now I need your help. So you can type your answers in the chat. So clearly we need the traditional classes, the dog and cat. So what else class do you think we need?
So
I think
some replies in the chat are all other
okay.
colors.
Oh, other color, yes, like blue, brown. I don't think they're blue though. So white, brown, black maybe. Yes, that's pretty much I am thinking. So I think this is my answer. So I think first we need a orange cartoon dog, maybe a brown cartoon dog, a white, or maybe some white real dogs, right? So and we find out the correct class. So this is actually the point I want to make. So the challenge of supervised learning. So in supervised learning, when we have a well-trained model on one task, if we wish to perform on any other task, even a slightly change, like from dog to an orange dog, we need to build a new data set. We we add in new labels and we retrain the model. So supervised learning is pretty inflexible. It doesn't like changes. And how do we fix this? So actually, one type of unsupervised learning that can give us this flexibility and ability to generalize the model to other different tasks. For example, here I use a BERT model in NLP area. So NLP stands for natural language process. So in NLP, we want the computer to have the ability to understand the text and spoken language like human being can. And BERT model is one of the famous model in NLP area. So what gave BERT model the flexibility is this pre-training and fine-tuning structure. You can see there's a separation between training and the testing stage. And to a BERT model, in the pre-training part, the model is trained on one task called the NSP, stands for next sentence prediction. So what we do is we give the model 2 sentences, and we want the model to tell us whether this second sentence is falling to that first sentence. And another task that BERT is trained on is called mask language model. So we mask some word in a sentence and let the model to predict it. Then after the pre-training or the training, so the model will understand some of the structure and the meaning of the sentence. Now we can use it to do testing. So it can be used on some completely different task. Here, this is a task is called squad. So we give the model a paragraph, a question, and a bunch of answers. We want the model to tell us which is the best answers. And another task is called NSE, stands for name entity recognition. So we give the model a sentence, and we want the model to tell us which one is a subjective, which one is a verb, which one is an object, so something like that. So you can see the BERT model is never trained on this task. So this pre-training and fine-tuning separation make it flexible. We only need to train the model one time, and we can use it on any other different task. So without doing a expensive training. But this kind of structure, they are usually used in NLP area, at least in 2021. In computer vision area, we still use the supervised learning. So if we can use this pre-training fine-tuning structure in computer vision area, then we will have a flexible model. And that is one of the motivation of the CLIP paper. So if we are going to use this unsupervised learning structure, we do not need labels, but we still need some kind of supervised signal or supervision, as they said. So what type of supervision can we use to help us train the model and tell the model the right direction to go? And also, it would be much better if this area has been well studied. So the team from OpenAI thought that row sentence related text that describe the image may be a good choice. So we can easily get millions of image and paired sentence. And since this row sentence or natural language have some connection to the picture, we may get a powerful model. So if our model can make use of those natural language as a supervision, after the training, the model may have the ability to connect image and text. So the question now is, can we use natural language knowledge to help us train a computer vision model? So to answer this question, the team from OpenAI, they bring out this CLIP paper. The title is Learning Transferable. So transferable means flexible. So learning transferable vision model from natural language supervision. And in this paper, they propose a model called CLIP, stand for Contrastive Learning, Contrastive Language Image Pre-training. And they did a lot of experiments. And perhaps the most stunning result is their result on ImageNet dataset. So ImageNet dataset is a collection of 1.2 million image, comes from 1,000 labels, 1,000 class. And they said they're doing something called zero-shot classification on this ImageNet dataset, but the CLIP model never seen those 1.2 million samples, but it has a similar result with a model called the ResNet, which is a baseline model, and it's a supervised learning model. So this ResNet model have seen those 1.2 million samples. It was trained on the ImageNet dataset, but the CLIP model is using a technique of zero shot. It doesn't see those 1.2 million image, but they have the same result. So to understand why this is stunning result, we need to understand what is zero-shot learning. So zero-shot learning in one sentence is a learner is given 0 examples from class, which were not seen during training. Here is a picture from the paper. So if you understand this picture, you will understand the zero-shot learning. And here is how this picture made. You have here. They have 4 well-trained. They are well-trained. They are finalized. Their well-trained model contains the ResNet and the CLIP. And you give these 4 models a lot of data set that they have never seen before. So you should notice that this data set they have never seen before. So you calculate the average accuracy and plot them in this graph, in the y-axis. And for the x-axis, because this model have never seen those data sets before, so if you give the model 1 examples or maybe 2 examples, it will it's seen some example in those data set, so it will perform better intuitively. And that is how they made this graph. If you give them more examples, they will perform better. And right now, let's ignore this line. So and CLIP paper, the zero-shot CLIP model, it can do zero-shot learning. That means it doesn't need to see any examples. It can do classification right away. So that is the meaning of zero-shot. So you don't need any example from those data set you have never seen. You can do the testing right away. That's called zero-shot. And to compare those to compare the performance of ResNet and the CLIP, just like they did in the paper, you should notice that these 2 models don't have the same condition. So for ResNet, it is already trained on the ImageNet dataset. Now you can think of the training process of ResNet model this way. So this is not what happened in the real world, but it will help you understand this. So before the training, the ResNet model haven't seen any image from the ImageNet dataset. As the training proceed, it's seen 1 example, 2 example, and since there are 1.2 million image in total and 1,000 class, so it will see about 1.2 thousand examples per class, and we calculate the accuracy. So you can think of the training of ResNet model as you can think of it's doing 1.2 thousand shot learning. But here the CLIP model, on the other hand, the CLIP model, it's never seen ImageNet dataset before. It is doing zero-shot classification, but they have roughly the same accuracy. This is long thought to be impossible. So now I want to show you some other amazing result and interesting application. But before that, I think a brief introduction to its structure maybe help you understand this and help you understand why and how the model did that. So like any unsupervised learning, the CLIP model consists of 2 parts. The first part is pre-training part. So I will talk about this part later. But right now you can think of it like this way. So they're using a technique called contrast learning. They carefully designed a task called image text pairing. So after the pre-training, you will have a text encoder that can turn sentence into a vector, and you have an image encoder can turn image into vectors. And if this sentence describes this image, or if they are matched, then the similarity between those two vectors will be high. So in a word, after the pre-training, you will have a model that understands some connection between image and task. So as I said, I will talk about this part later. Now let's focus on the testing part now. So let's say we're using CLIModel to do classification. And notice that the CLIModel never trained on classification task. So how does it do classification? Here, let's say we are doing classification on ImageNet dataset. So we will have 1,000 labels. And the first step, they need to change those 1,000 labels into 1,000 sentences, like a photo of a plane, a photo of a car, that kind of sentence. Then we are using the text encoder that we have here to turn them into 1,000 vectors. And we are using the image encoder to turn the picture that you want to classify into a vector. And now we are trying to find like to which of the label is this image close to. So in this case, this sentence or this vector have the highest similarity. So this image will be classified as a photo of a dog. This may not be very surprised, but what's amazing is this structure is not bounded by the number of categories. If you are using a supervised learning model, let's say we're going to predict what class is this picture. If you are using a supervised learning model, we are bounded by those 1,000 categories. The best a supervised learning model can tell you is maybe this is a photo of a line. But if today we are using the CLIP model, we can add as many new categories as we want. For example, I want to add those two labels. So similarly, the CLIP model will turn them into sentence, a photo of a logo of a line, a photo of a blue and white logo, and using the text encoder to turn them into some vectors. And maybe today, the model will tell us this vector has the highest similarity. So it will tell us this is a photo of a blue and white logo. This is much flexible than supervised learning because we can add more labels. So right now I want to talk about some result and applications. The first one is the CLIP model has a powerful transfer learning ability. Here you can see in this picture, although CLIP model and ResNet, which is a baseline supervised learning model, they have the same similarity on the ImageNet dataset, but if we change the dataset a little bit, ResNet will perform poorly, but CLIP model is still powerful. And also, if we constrain the CLIP model here, they are using the CLIP model to do zero-shot learning, but we let the ResNet model to do fine-tuning. It can be tuned. And you can find the CLIP model wins, they're comparing 27 datasets, and CLIP wins 16 of them. Also, if we allow the CLIP model to do fine-tuning, that means it can see more examples. It will outperform the best model in that time, this efficient data in 2021, this is the best model. So it can outperform this model on 21 out of total of 27 data sets. So in a word, if we constrain the CLIP model to do zero-shot learning, it will match the baseline model. If we unlock its full potential, it will be the state-of-the-art model in that time. The second result is flexibility when we do object detection. So for traditional method, a method can only tell you like these three examples are toys from its base categories. But this team from Google, they're using CLIP model to do object detection, and they detect novel categories like toy dogs and maybe green toys. So they detect some novel categories. Also, because the CLIP model using tags as a supervision, so we can use tags to guide image generation. For example, here, this team wanted a picture of a horse eating a cupcake, and they get this picture, and a temple, they get this picture. So I would say this result is pretty realistic. Also, here, this application. So CLIP model can use to do style transfer. For example, here you can give them a picture and want a new haircut, and maybe remove the makeup, and maybe change the tiger to a lion. Or maybe they make this cat more cute. So this is fine. This is fun, but it also got me thinking like it may be a threat to the insurance company like us. So I think one can easily make up a counterfeit recipe using this tool. Counterfeit like receipt or some documents. That may be a problem. Also, the next application is video recognition. Yeah, this is my favorite one. So using this tool, you can feed the model a video and let it find an object. For example, here you give the model a video and said you want a truck with a tag called Old Vela, and the model will output this keyframe to you. Also, maybe a white BMW car, a bicyclist with a blue shirt, or a blue smart car. I think this may be useful for us. Like in the future, I no longer need to watch the whole movies just to find my favorite movie clip. So I like this one. Okay, now let's talk about how the team from OpenAI make these things possible. I will talk about the key part of the whole model, the pre-training part. They are using a technique called the construct learning. So right now, let's see what is a construct learning. In a more intuitive way, we can think of like this way. Here, let's say we have three pictures. These two are electric guitar, and this one is electric bass. So I can say actually we do not need the model to tell us what is the specific model of these pictures. If a model can understand that these two images are similar and they are both different from this one, then I would say they understand what is the guitar and what is the bass. So to be more specifically, like we're doing contrast learning. So we are working with vectors. So first we need to turn those pictures into vectors, whether you're using a convolutional network or vision transformer or anything you like. Now to achieve this effect, actually we need a vector in the embedding space. We need these two vectors to be close, and they are both far from these vectors. If we can do this, then the model understands what is similar and what is different. And that's pretty much the contrast learning. Now, before I give you the formal definition, we need to know this terminology. So in contrast learning, if two vectors that are from the same class, or they should be similar, they are called a positive sample pair. And any vector that are different are called negative sample pairs. So these are all negative sample pairs. So now let me rephrase the goal of contrast learning. So in contrast learning, what we are doing is we trying to bring the positive sample pairs as close as possible and bring the negative sample pairs as far as possible. Now let's talk about how do we do the training. So for every training, we need a loss function that can tell the model which is the right way to go. So this one is a commonly used loss function in contrast learning called InfoNCE loss. Now, if you are familiar with classification, you will find this equation is very similar to cross entropy, but it's perfectly okay if you don't know that. Here, the Q in this equation stands for the query or the vector that we want to change. So, and K plus and Q, they form a positive sample pair. And Q and other K, they form negative sample pairs. So after the training, this vector that we want to change should be like right here. So it's close to the positive sample pair and far from the negative sample pair. Now, if I say this loss function can help us finish this goal, I'm sure you don't believe me, right? So I made a table here. Let's check our goal one by one. The first goal of contrast learning is we want the positive sample pairs to be close. If they are close, that's good. So positive sample pair to be close, that means the similarity or the inner product of these two vectors is large. And from this equation, we can say if this term is large and there's a negative sign, the loss will be low. And a low loss means we do not punish the model. And we do not punish the model because positive sample pair close is a good thing. So we check this. Our second goal is if the positive sample pair are far apart, that means the similarity or the inner product here is small and there's a negative sign, so the loss will be high. And we punish the model because we want them to be close. And our third goal is if the negative sample pairs are close. So if Q and K1 or maybe Q, K3 they are close, then this term will be very large. And this is in the denominator and this is a negative sign, so the loss will be high. So we punish the model. That because we want them to be far apart, not close. The fourth one is the similar if they are small. If every Q, K1, Q, K2, K3, they are all far apart. Their inner product is small, then within the denominator there's the negative sign, so the loss function will be low. And we do not punish the model. And that's a good thing. So right now, I think you are convinced this loss function can help us do the contrast learning. Yeah, so hopefully this vector will move to here maybe. Now let's go back to the CLIP paper. How do they do the contrast learning? How do they define the sample pairs? So very intuitively, if a sentence and a image, if they are matched, if this sentence describes this image, then they are considered as a positive sample pair. If this sentence does not, that does not describe this picture, they are negative sample pairs. So here they turn, let's say we have 100 sentence and 100 paired text. And we use a text encoder to turn them into vectors in the embedding space, and an image encoder to turn them into embedding space vectors. If these two are matched, they are the positive sample pairs. So here we will have 100 positive sample pairs, and we'll have n by n minus n, so that's 9,900 negative sample pairs. You can also look at the pseudocode that will help you understand this better. So from the beginning, the image we have is this dimension. We have n image. Each one is a dimension of HWC, stand for height, width, and color channel. And we'll have n sentence. Each one has a length of L. And we're using an image encoder and text encoder, like here. We turn them into in their dimension into an image. Each image has a vector has a dimension of di, and n text vectors, each one has a dimension of dt. And because we want to do the inner product in the embedding space, they need to be in the same dimension. So here they do a linear projection to turn those vectors into the same dimension. Here the wi is a linear projection that turns the dimension of di to de, and wt turns the text vector from dimension dt to de. So right now they are in the same dimension. We can do the inner product and use the loss function that we have talked earlier to do the training. So this is pretty much is the CLIP model. The idea is very simple. They're using contrast learning to do these things. And at the end, let's talk about some limitation of this model. So the CLIP model is powerful, but it's not perfect. They said they can beat the state-of-the-art model in 2021, but right now, I think the state-of-the-art model on ImageNet dataset will have more than 90% of accuracy. So it's not perfect right now. The second limitation is the CLIP model is still a deep learning model, so it relies heavily on the data set. And very interesting part is the CLIP model has only have 88% of accuracy on MNIST dataset. So MNIST dataset is like this. They are all digital handwritten images. Any like very simple model, like a convolutional network, it will easily have a 97 or 98% of accuracy on MNIST dataset. But even you are using the linear regression on the image, you will have maybe a 90% of accuracy. But we don't know why the CLIP model perform not so good. So the team from OpenAI, they look at the data set they have. They find that every image they collect is from the daily life object. There are no such picture like these things, like artificial handwritten digit. And also there are no sentences that describe this kind of image. There are no such sentence like this is a handwritten digital number 7 picture. There are no such sentence. So that's why the model is confused on this kind of task. Oh, and the third limitation. So I barely talked about how they train this CLIP model, what kind of training resource they are using, because I doubted that someone could replicate their result. And if you are familiar with deep learning, you should know there's a 2017 paper called "Attention is All You Need." In that paper, from Google, they propose a structure called a transformer. Actually, the letter T from BERT and like ChatGPT, the T stands for transformer. So transformer now is very widely used. So transformer is all you need. But I would say money is actually what you need, because training a transformer model is extremely expensive. In here, the OpenAI, they collect 400 millions of paired image and task to do this training, and they are using a training epoch of 23. That means the model will see all these 400 million image 32 times. That's 1.2 billion image. And if a model can process one picture per second, that will take 400 years. And another thing is they use a mini batch of size 32,000. So mini batch, the reason we have mini batch is because 400 million images is too much for the memory. So we use mini batch so that the model can only see one batch of image per time. But the mini batch of 32,000 is not a mini batch, definitely not a mini batch. And also the training resource, the V100 GPU is probably the best one you can get, and they are from NVIDIA, and each one is, I think, maybe $4,000, and they're using 600 of them, and training this model takes 18 days, and that's only for one pass of the model. If they're going to tune the hyperparameter or something, that will run it lots of time. So I'm sure they spend months or maybe years on this project. So yeah, that's pretty much the CLIP model and my presentation. Thank you.